Good morning. I am doing the pre-party a little bit different. After Monday's lecture today, I didn't feel like we got to where we needed, and there was still some confusion or hesitation of thought process as it related to fats, specifically triglycerides. So today's pre-party is all about understanding the basic structural unit of triglyceride, and then at the end relating that to what we know as trans fats. If you are comfortable with these topics, don't feel like you need to watch this pre-party. If you have any questions about these topics, this pre-party will hopefully help you answer those. So in basic, simplest shape form, a triglyceride is a cholesterol backbone represented by that orange box you see on the screen, and 3 fatty acids attached to that cholesterol backbone, represented by those blue ovals. Now in the body, this is not what they actually look like. Those shapes, the oval and the rectangle, are made of atoms. And we know from last time's pre-party, fats are made of carbon, oxygen, and hydrogen. So if we break apart the red or the orange box and the blue ovals, we will start to see how the atoms are aligned, which will help us in understanding structure of a triglyceride. In looking at just the glycerol backbone, that orange rectangle, if we were to put atoms to that, it would be a CCC chain, 3-carbon chain, attached to hydrogens and hydroxyl groups. I think after today, most of us were comfortable with what a glycerol backbone is. The confusion came in discussing the fatty acids, or those individual blue ovals. In simplest form, fatty acids are what you see in pink there, a carbon bound to an oxygen through a double bond, and then bound to a hydroxyl group through a single bond, and an R group through another single bond. That CO and OH, that is called a carboxyl. That's important because when we combine the glycerol backbone with the fatty acid, we release water, and that water comes from that carboxyl. What changes from fatty acid to fatty acid, even in one single triglyceride, or if I had a million triglycerides surrounding me, the changes come from the R group on that fatty acid. I've gone ahead and drawn a saturated fatty acid. So this is essentially one blue oval that we're talking about. This is a saturated fatty acid because it is a carbon chain. You see that in the black ink. We have a 5-carbon chain fatty acid. I've gone ahead and put the carboxyl group in blue. That's not going to change through the rest of our discussion. The carboxyl group will stay the same when we're talking about an individual fatty acid. So we know this is a saturated fatty acid because it is surrounded by hydrogen atoms. So we see each carbon has a hydrogen bound to it, and that is because carbon binds to 4 different things. Always in nature, carbon has to bind to 4 different things. If it is only bound to 3, it will do anything in its power to find a 4th bond. It will never bind to 5 different things, okay? So that's important, so keep that in mind. If we look now at an unsaturated fatty acid, that's the next classification. We have saturated versus unsaturated. Unsaturated means we have gone in here and created a double bond between 2 of the carbons, at least 2 of them, okay? And in doing so, we see that this carbon here bonds to the carboxyl group, that's bond 1, hydrogen, bond 2, and then twice to this neighboring carbon, so that's 4 bonds. So that is why we don't see any hydrogens down below, so it can only bond to 4 things. Now we draw this in a straight line. In actuality, anywhere you see a double bond, we see a bend in the structure. So what you see on the screen now is pretty correct for the most part, but in the structural integrity, it is incorrect. So if I were to redraw that, same chemical composition, every time we see that double bond, we see a bend. So that's why you see it coming down to the right lower corner of the screen. And it does that because those 2 hydrogens on top of the carbon really don't like being next to each other. They are not friends. So they want to push themselves apart. And that's why we see the bend. Okay, so in an unsaturated fatty acid, it is not a straight chain. There's somewhere in there a bend. If it is a polyunsaturated fatty acid, we see many bends in that chain, okay? All right, so again, let's continue talking about that unsaturated fatty acid. Here we notice we have 2 double bonds between 2 different sets of carbons. So again, we see more bend because these 2 hydrogens are repelling each other, and these 2 hydrogens are trying to repel each other. Again, if we count all the bonds associated with each of these carbons, they are bound to 4 different things. So this is a polyunsaturated fatty acid. Now, why have I spent so much time talking about this, summarizing, talking through each of you in your groups today? It's important because everything we see in physical properties of fat is due to the structural shape of those fatty acids. So put one way, a bent lipid will melt at a lower temperature than a straight lipid. Okay, so bent, meaning unsaturated fat or lipid, will melt at a lower temperature than a saturated lipid. Okay, or we can put it on that third bullet. Unsaturated fat, that would be a bent fat, is liquid at room temperature. On the flip side, a saturated fat is solid at room temperature, meaning vegetable oil comes in a bottle, right? If we were to open that lid and pour it on my desk, it would come out almost like water. It's going to flow across any part of the desk. If we were to take a can of lard cannot be poured out. We have to scoop it out with a spoon. That's because lard has a higher concentration of saturated fatty acids. So remember, in the last couple of slides, all of those diagrams, I was talking about one individual blue oval. That's an individual fatty acid. But when we make a triglyceride, we are connecting 3 individual fatty acids to that glycerol backbone, or that orange glycerol backbone. So if we have 3 saturated fatty acids, they can stack up very neatly. There's no trouble for them to be in a very uniform shape. And that shape is represented by a solid physical character. However, if we were to place that top fatty acid with an unsaturated form, we see that bend causes some spatial problems, right? Though there's no longer a very uniform, even stacking. So what we see is that these become more liquid or fluid because there's room for these things to move around. Back here, there's really no room. They don't want to move around. It's all going to be fine that they're stacked on top of each other, and they're fine being solids. Here we start to see more liquid physical character because this unsaturated fatty acid. So now the next question is, we can make an unsaturated fatty acid that typically has a bent shape into a straight shape. And we do this because we want to take liquid fats and put them in a solid form, because that solid form is more ideal for making certain types of food. So food manufacturers are going to take liquids that are higher in unsaturated fatty acids, hydrogenate them, and make them solid forms. So through hydrogenation, we can get 2 different products. First, we can just add as much hydrogen. That's where we get hydrogenations from. We're just adding hydrogen into that liquid and make it a saturated fatty acid. That's where all these carbons are bonded together only singly, and they're all surrounded by hydrogens. Or through regulated processes of hydrogenation, we can keep the double bond of the unsaturated fat, but we force the 2 hydrogens on those carbons to be in opposite formations, meaning one's going to be on top of one carbon, the other is going to be below the other carbon. So in this form, these 2 hydrogens are as far apart away as they can get. They like that. They want their own space. They have no problem. So that those carbons don't have to bend to account for those hydrogens not liking each other. It can stay in a straight line. Okay, so through hydrogenation, we're changing the shape of that fatty acid from bent to straight, and that will allow any sort of trans fat, which is this molecule down here, trans fat, because these hydrogens are on the opposite side of the double bond. That trans fat can be solid at room temperature. That's probably the number one reason we hydrogenate foods. It will also stand up to a higher cooking temperature, so it takes longer to melt at higher temperatures, so we can cook a lot of things in that range, that variation of temperature range that we get from moving it from a liquid to a solid form. And it will stay fresher longer. So if you have a tub of margarine, oftentimes it will stay fresher than a stick of butter that is truly only a mixture of polyunsaturated, monounsaturated, and saturated fats. Okay, so that is the reason we hydrogenate. Now, I think we covered enough as to why we won't include trans fat in a food label or in a food due to health effects. And if you need to answer more questions about that, look at the mini lecture that I posted on Wild Courses. My hope is this has kind of cleared up some muddy points in what I saw today after leaving class and reflecting on how class went. If you have further questions, feel free to ask. Now on Wednesday, we will start to discuss how all of these things, fatty acids, glycerol backbones, triglycerides, relate to food. And our model is going to be seafood, because seafood has a certain type of fat that makes it beneficial to include in our diet. Okay, so we will see you on Wednesday.